This will be AP Chemistry Notes, pages 15 through 18. And I start with a little review. What is resonance? And realize the electrons are moving and being shared, but the protons stay put. Well, the nucleus stays put is actually a better way to phrase it. Also, in our last lesson, we found out that beryllium and boron don't fulfill the octet. Often, we find that beryllium is actually okay with 4 valence electrons, and boron is okay with 6 valence electrons. And so these are more examples of a deficient octet. Now, some terms that come up is it's possible to get confused between isomers and resonance. Resonance is the same molecule, but we draw it in different ways to help explain it. Whereas isomers are different molecules, and you typically see that in organic chemistry. And I have kind of a silly example here with the ABB and the BAB. In this case, if B and A were different atoms, this example in number 3, these would be different isomers, and that's not resonance. The only reason I bring up isotopes is because it sounds like isomers. And just to remind you, isotopes are different versions of the same element. So they have a different number of neutrons. And that causes different versions of the same element, like carbon 12, carbon 13, and carbon 14. Now, something you've probably not heard of before are what are called sigma and pi bonds. And what this is used for is to help describe how covalent bonds are sharing the electrons. Now, a single bond is the same thing as a sigma bond. And I have a drawing here. If I have atom A and atom B, these electrons that are being shared between the two are said to be a sigma bond. And the symbol you'll see is this weird little thing like here. It's a Greek sigma. I think of it as the number 9 that kind of fell over on its side. That's how I remember it. And then when you make a double bond, the problem is this space is already occupied in the middle. You can't put more electrons being shared in here. That's already taken. So what happens in a double bond, since they're sharing more electrons, is you need to use the space above the atoms and below the atoms. Or if you preferred, you could use the space in front of the atoms, that's in front of our screen, and behind the atoms. This is one's just easier to draw. And this is referred to as a pi bond. And what it means is that these electrons are not being shared directly between. That space is already taken by the sigma. And now space is being used above and below, in my case here and here. Now note, what I have shown here is one sigma bond here and one pi bond. Part of it is up here and part of it is down here. And I had a student one year, as I was teaching this, they said they thought of the pi bond as a hamburger bun. They thought of the sigma bond as the stuff inside the hamburger and the pi bond as the bun. And so my drawing right here is showing one sigma in the middle between the A and B atom and one pi that's above and below. Those are the regions of space being used. A triple bond has 2 pi bonds. So what would happen in this case is we now need to use a new area of space. And so in 3D space, the second pi bond would take place in front of these two atoms and behind these two atoms that I can't draw. Fortunately, I have some diagrams that help show this a little bit better. Go over here. This picture shows the sigma bond in the middle between two carbon atoms. So here's the sigma space. And then it shows a pi bond, part of the space being used up here and part of it being used down here. If we go to a triple bond, we have this scenario here, in which here's the sigma between these two nitrogen atoms. And then one of the pi bonds, let's use green, is here and here in the back. The other pi bond is in the top and in the bottom, like that. Which makes sense because, of course, N2 molecule has a triple bond. So next I have an example. Determine the number of sigma and pi bonds in C3H6. Now, something to notice with C3H6, and I know this is a little bit of a struggle this year because not everybody did organic chemistry last year, is when you have a molecule like C3H6, the pattern of the number of carbon versus the number of hydrogen tells you something. And just sticking to the basics, the fact that the number of hydrogens is double the number of carbons means there must be one double bond present. And of course, even if you don't realize this and you try to draw this molecule, you'll go carbon, carbon, carbon. You'll stick your hydrogens off of it, which I just happen to do like this. I'm not going to bother putting the H's. And then you would realize that I shouldn't have that bond right there. Let me fix that. And that in order to keep these left two carbons having an octet, I would have to add a double bond here. And so the question says, how many sigma and how many pi? Well, when you go to count the sigma, you count everybody. So 1, 2, 3, 4, 5, 6, 7, and 8. Two, 3, 4, 5, 6, 7, and 8. And then you also count the double bond. I've already counted this as a sigma. And the extra bond in the double bond right here would be 1 pi bond. And that's why the answer is 8 sigma and 1 pi. Moving along, when you get to molecular geometry, when you're asked to explain why a molecule has a particular shape, it can be useful to mention the VSEPR theory. And if you want to spell it out, it's valence, shell, electron, pair, repulsion. And what it means is that atoms are going to repel each other, and electron pairs are going to especially repel each other. And I have a more formal definition right here that you should read. And an interesting example comes up if we take an example of a tetrahedron right here versus a triangular pyramidal versus a bent. You'll notice that all three of these structures have 4 items joining the central atom. In the tetrahedral, we have 1, 2, 3, 4 molecules, 4 atoms. In the case of the triangular pyramidal, we have 1, 2, 3 atoms and a lone pair. And in bent, we have 2 joining atoms and 2 lone pairs. I made a note, some people call this the alien lobe for the unshared pair because it kind of looks like a little alien head. So if you hear me mention that in class, that's what I'm talking about. And you'll notice in the tetrahedral, assuming that all 4 atoms are the same adjoining atom, so let's say something like CH4, the best arrangement spreading the 4 adjoining atoms out is 109.5 degrees in 3D space. But if we add this unshared pair of electrons to replace one of the atoms, it especially repels the 3 atoms, and now it decreases to something like 107. And these bond angles, they vary from molecule to molecule, so these are just rough guidelines. If you add a second pair of unshared electrons, it gets even less, 105. So to give you some examples for these ones, this first one you can think of as CH4. The second one you can think of as NH3. And the last one would be H2O, if you want examples to go with these drawings. Now this leads us to the different molecular geometries. You should know 5 already from first year chemistry, and we will include those 5, but we're also going to do a few new ones. And the main thing here is not so much being able to say what the right name is, it's being able to explain why it has that name. Notice I mentioned over here, the terminology can vary a little. Some people say triangular planar, or in this case, trigonal planar. I often say triangular, angular, instead of trigonal. And you can use either one, whichever one works for you. So just kind of go along with whatever the terms are. So we have linear here. And normally you don't need to memorize the bond angles. You just need to use common sense and geometry and figure them out. Here we have triangular planar, which of course 120 makes sense. Tetrahedral I've already talked about. This is a new one, triangle, bipyramid, or triangular bipyramidal, or whatever version you prefer. You'll notice there's 2 pyramids, one pyramid on top, one pyramid on bottom, and they're both joined in a triangle here, here, and here. Hence the name triangle, or trigonal, or triangular bipyramid. We move along. This one might have the best name of all, octahedron or octahedral. And you'll notice what's weird about this is there aren't 8 atoms. You might think, oh, octa, 8 atoms. If you count it up, we have 1, 2, 3, 4, 5, 6, 7. And you might be thinking, this thing's not named correctly. The names don't come from the number of atoms, they come from the number of faces. If you made this out of pieces of cardboard, for example, if you actually made this shape, you would have a face in the back of the top structure, and then you'd have a face in the front. You'd have this little one on the side, another one on the side, and then there'd be one, like I mentioned, in the back that I can't draw very well. And so there would be 4 faces on the top half, and there would be 4 faces on the bottom half. And that's what it's named for, are the number of faces, as if you were making an actual structure of these things. And that's why octahedron makes sense. Now, as I mentioned, this is a weird bent. Normally bent has a bond angle of somewhere around 105, because you have something like water, in which you have two unshared pairs of electrons out here really causing a ruckus in the molecule. This is a special case, like I have here, like nitrogen dioxide, in which the nitrogen only has one unshared electron. So it does cause these two oxygens here and here to get squished a little, but not quite as much as you would have like in a water molecule. Here's triangular pyramidal, which is an old friend. Next, we have a distorted tetrahedron or seesaw, because if you orientate it correctly, it kind of looks like a seesaw. Distorted tetrahedron, I think, makes more sense because you have 1, 2, 3, 4 adjoining atoms, and then you've got an unshared pair of electrons over here that's distorting it. I go to the next page. I think this one's my favorite. It's a tie between the square pyramid and the weird linear that's going to come up. I like this one because it kind of looks like I think it looks like the lunar lander. It looks like a little spaceship right here. And then I think of this as like the little rocket on the bottom of the spaceship. And the name makes sense. It's a square. It's got 4 adjoining atoms forming the square. 1, 2, 3, 4. And you've got one up top, a 5th adjoining atom. That causes it to be the pyramid, and the unshared pair of electrons on the bottom that I refer to as the little rocket. Here's the classic bent, like water. Continuing along. This one's often called T-shaped. It's not really drawn T-shaped. It'd be more T-shaped if it was drawn like this. That looks more like a T, and you'd have your unshared electrons out here like that. This one here is square planar. It forms the square in the middle and has an unshared pair of electrons above and below. And then this is the other one I really like, just because it's so odd. It's linear, and you only have 3 atoms, which linear often is, but it has 3 unshared pair of electrons, and they kind of make this donut shape around the center, which keep the 2 adjoining atoms sticking straight out. All right, that's enough shapes. There's something in the notes right now that says, when answering geometry questions, it's always a good idea to draw the Lewis structure. If nothing else, it'll help you. If you can, use the VSEPR concept. You don't need to spell it out. You don't need to say valence shell electron pair repulsion. Just say, according to the VSEPR or VSEPR concept, atoms orientate as far as possible, and they orientate especially far away from unshared electrons on the center atom. And you want to focus on the center atom and what's happening around it. Listing the shape can be useful as well when doing that. In this class, you won't often be asked what is the shape. You'll be told the shape, and you'll be asked, well, why is it this shape and not another shape? So if I go back to a classic example, you might be given something like in H3, and you might be told, well, we could do this with it, and we can do this with it. It turns out the correct response is this, and the question would ask, why is NH3 triangular pyramidal and not triangular planar? And what would be really nice for you to do is draw both Lewis structures and then mention that this doesn't have unshared electrons on the center atom, but the triangular pyramidal would have unshared electrons on the center atom, and they're pushing these 3 atoms down, which cause it to be pyramidal, according to the VSEPR theory, etc. Next, and last thing for this lesson is polarity. Now, polarity is a huge concept. Polarity helps explain so many things that we observe in our daily lives and so on. It really is an important concept. Right now, the goal is not really to explain things in our lives, but to explain why a certain molecule is polar versus another one. So what it is an unequal sharing of electrons in a molecule. Sometimes you'll see it referred to as the dipole. And it helps to have electronegativities available, and you're going to want to know the geometry as well. Otherwise, it's hard to do. So my recommendation is draw a Lewis structure first, determine the shape, and then draw the individual bond dipoles. And the way to do that is with the arrow that I have here. So if we look at these examples, we'll start with this one. 2 hydrogen atoms, they're going to share evenly. Neither of them has a higher electronegativity, so there's no bond dipole to draw, and thus this must be a nonpolar molecule because they're sharing equally. There are no poles, and it's that simple. It's called polar if it has poles, a positive pole and a negative pole. If we look at the second example, fluorine has a higher electronegativity than hydrogen. And you can know this by looking at the periodic table and knowing the pattern, or by looking up the actual values. So what I recommend you do in this case is draw this arrow like I have here. And when you draw the arrow, point it towards the higher electronegative atom, and then put this little dash across the back. By doing your arrow like this, what it does is 2 things. It makes it not look like a bond, and it also reminds you that this side of the molecule is positive because that kind of looks like a positive. And the result is that in this molecule, HF, the fluorine is going to be a bully, and not only does it have its own electrons, but it is going to hog the shared electrons in the bond, and that's going to make the left side slightly negative and the right side slightly positive. Now be aware, these are not ions. This is not a complete +1 and -1. That's not how strong this is. It's weaker. So that's why I say slight negative here and slight positive here. And the way to show this and make it not look like an ion is to use a lowercase delta. Now you know an uppercase delta is a triangle. A lowercase delta is like this. You can think of it as a number 8 that you didn't finish, or the letter S that got a little crazy at the end and had an extra swoop. And it's something like that. And what you do is you put this lowercase delta with the negative and positive poles. And the negative always goes where the arrow is pointing, and the positive goes where the positive side of the arrow is. I've got water here. In this case, there are 2 bonds, both of them being polar, or you could say both of them have a dipole. I have drawn the dipole with the arrows. They both point towards oxygen. So what I like to say is I like to refer to as the overall arrowness. The overall arrowness is pointing up, which means the top will be negative and the bottom will be positive. And I've seen this done a couple different ways. I've seen some people put a positive by both hydrogens, and I've seen other people do this, where they simplify things and they say, oh, well, here's negative, and they just say the other side's positive. And I'm okay with either of those. Now, polarity is not a hot and cold thing. It's not as simple as you're polar or you're nonpolar. If there is polarity, there's a range. So if you have to rank things, just look at the significance or difference in the electronegative values to determine which molecule is more polar than the other. And these are some approximate numbers that can help assigning whether a bond is polar or not. If it's 0.5, the difference between the electronegativities of the atoms or less, then that's typically considered a nonpolar bond. Anywhere from 0.5 to 1.0 is slightly polar. Above 1.0 is more significantly polar. And above 1.7, you usually don't even have a covalent bond at that point. But this situation, what you usually have is that one of the atoms has given the electron and the other has taken. So once you get above that difference, you usually have a situation like sodium and chlorine, where sodium has just completely given an electron to chlorine. And this isn't a polar situation. It's not even a covalent bond. In this situation, you have a positive one ion and a negative one ion, and that is a completely different discussion. I've got a little practice here, and you can see how I've drawn the arrows. In this example, CH4, the arrows end up canceling. There's a down, an up, a left, and a right. You're technically supposed to do this in 3 dimensions, but even if you do it in 2 dimensions, it works. And since the arrows cancel each other, it is nonpolar. Here, CH3F. The down and the up arrows cancel, but the right and the right don't cancel. So the overall arrowness is to the right, meaning the right side is negative and the left side is positive. And since it has poles, it is polar. BF3, your first thought might be, wait a second, your Lewis structure is wrong. Boron doesn't have an octet. But go back to the prior lesson, we talked about boron. Boron's special. It's okay with 6 valence electrons, which it has. So this is the correct drawing. It's not as obvious here, but these 3 arrows cancel. If you just draw the arrows by themselves, like here, here, and hopefully you draw your arrows straighter than I do, these arrows cancel each other, and thus the molecule is nonpolar. And then I have another one here with CH2O. The overall arrowness, as I've drawn, is straight up, and thus it's negative at the top, positive at the bottom. It is polar. And this is just a term to know. Sometimes they refer to this. If you're polar, you have a dipole moment. If you're nonpolar, you don't. Just a word to be aware of. Here's some notes. These molecules have to be polar no matter what else happens. They're asymmetrical and they will be polar just because of the unshared electrons. And I mentioned these terms already when I talked about the prior example. I have an example down here as a little bit of practice. I encourage you to try this, take this, and go through these steps. Draw the Lewis dot, determine the hybrid, go through sigma and pi bonds, determine the shape, determine if it's polar. And like I mentioned, it's a tough one. And I really like this example because it's important that you do every one of these steps in order to fully understand what is happening. Go through this, practice, see if you can do it on your own. I make a note that this one's tricky, that because it's asymmetrical, it would be considered polar. But I could see a student at our level saying nonpolar because it looks like the arrows cancel, but you have to factor in the arrows are not the same strength. This arrow is a more powerful arrow than the other 2, but that's okay at our level.